I was recently looking through this book on numerical recipes in C. C is, of course, a computer programming language. It's pretty antiquated. And this book, though, has a lot of very good C routines, particularly for scientific and numerical computing. So the reason I was looking through the book was I was curious about how difficult it might be to implement a fast Fourier transform algorithm in JavaScript inside the analog discovery. I've decided not to go that route for a number of reasons, including support and other things, but mainly because it looks like that Digital itself may be going to make some changes, so I'm going to defer any action there. But in the course of the of looking at that, I came across this chapter on the fast Fourier transform and was reminded of a topic that once consumed a fair amount of my time and effort, about 3.5 years in fact, and that is the issue of complexity in algorithms. And so I thought I might do a video on that. It's an area that's really kind of esoteric, and I realize it's probably outside the area of most people's interest. But while it was fresh on my mind, I thought, well, put something together. I'm going to stay very high level, try to do this from, 10,000 feet or so. But nonetheless, what I'm going to try to talk about is the influence of time complexity on computer algorithms. Here's a little overview of what this is all about, and don't be overwhelmed by the terminology. I'll try to explain in basic terms what this terminology represents, but we're not going to go into the mathematics here. We're just going to look at the issue itself. The issue is that whenever you're developing a computer algorithm, you need to be aware of how it's actually going to solve the problem as the problem gets larger and larger. In other words, there are some ways of attacking a problem that when you program it on a computer, it'll run forever without producing a solution. And by forever, I mean the lifetime of the programmer or longer. And there are some approaches to some problems that would run for the life of the universe and so on. So it is important that you think about this issue if you're developing algorithms. And so it's an area that I looked on YouTube. I could not find very much on it. There are a couple of videos, but frankly, most of those are either too mathematical or they don't offer enough examples to kind of bring it all down to earth. So in order to talk about this, I am going to have to talk about some terms. The first one is the idea of determinism or deterministic algorithms or deterministic problems. Those are problems that can be solved by a formula, and one of the best examples I can think of is the quadratic formula. If you know when you have a quadratic equation like this, there is a formula that you can use to solve for x in this quadratic equation, and depending on the values of a, b, and c. And you plug it in and it just gives you the answer. You only do one computation and it's done. Many problems, however, are non-deterministic. In other words, there's no known formula. Now, that doesn't mean that a formula can't exist. It's just that nobody really knows about it yet. And that's one of the issues in this whole area of complexity is there's a little bit of religion involved. I'll talk about that a little later. But an example of a non-deterministic is the traveling salesman problem. In other words, a salesman has to visit 50 cities over the next 2 weeks, and the question is, what order should he visit the cities in order to minimize the distance traveled? If a problem can be solved in polynomial time, then it's called a polynomial algorithm. An example is if n is the size of the number of variables, and you can solve it in n squared time. In other words, as n goes up, the solution time or the complexity goes up as the square of n. And of course it can be n cubed and so on. And that's normally called p time or polynomial time. If it is both non-deterministic and polynomial, in other words, there is a polynomial formula, but the problem is non-deterministic, then it is called NP. And NP falls into NP complete and NP hard. We won't talk about those. This gives you an idea of the solution space, if you will, for polynomial, non-deterministic polynomial, and non-deterministic polynomial complete. I hope you won't be turned off by all of this jargon. NP is the class of all problems that can be solved in polynomial time, but without a deterministic solution. It is believed that P is a subset of NP, and it is believed that NP complete is a subset of NP, and that NP complete and P do not overlap. The only reason that I go into all of this is what you will should seize on with that statement is the word believe. There is a lot of work on this in mathematical circles, and even to this day, no one has yet been able to prove that P is equal to NP or NP is bigger than P or lots of things. So why in the world am I going to such a long and quite frankly boring procedure? The reason is that computers can be modeled by a device called a Turing machine. This is named after a gentleman named Alan Turing, who was a British mathematician during the war, one of the people who helped, who worked on German codes, the Enigma and things like that. Very interesting person, very interesting story. There's a lot about the whole thing having to do with Bletchley Park and the development of digital computers and so on, and Turing was right in the middle of that. There is a thesis developed by a man named Church and based on the Turing machine, and that is that everything computable is computable by a Turing machine. Now you notice it uses the word thesis. That's another way of saying theory. It's not proven that this is true. However, to date, nobody has found a problem that is computable, that can't be computable, that can't be computed with a Turing machine. So the reason that this is of interest is this is a very simple model of what we call a digital computer. This is a book published by W.H. Freeman, the same people that published Scientific American, by Gary and Johnson on computers and intractability, a guide to the theory of NP completeness. And as you can see, when somebody writes an entire book on this subject, it's something of interest to a lot of people. It is fundamental to the whole idea of digital computing. So why in the world do I have books like this? Well, I once worked in this area, not so much in the theory, but in the application. In other words, the use of intractability theory or complexity theory and computer algorithms, and I'll talk about the area where I worked. The main reason I'd like to do this video, though, is to sort of talk about why this is important. If you're really interested in the technical details, we'll get a book like this one, or here is another one that was published by Springer Verlag by Kurt Melhorn called Graph Algorithms and NP Completeness. Nonetheless, where I'm really going is I'd like to talk about a series of computer problems that depend on the approach. Now, back in the early days of computing, one of the most important computer problems was the sorting of large databases so that you could search them efficiently. And a number of people developed a number of sorting algorithms. The reason is the early approaches would just run on and on and on. As the database grew larger, the computer was running into the night and then through the next day and then for a week and sometimes for a month just to do all the sorting. And so people began looking at that and they came up with a number of solutions. And this book by Donald Knuth that appeared in 1973 is one of the synopses of how people were able to solve sorting problems in less than polynomial time. Another area that actually began back in 1965 with a couple of gentlemen named Cooley and Tukey is the idea of a faster way to compute a Fourier transform. Now, the fast Fourier transform was developed. This is a book by a guy at E-Systems. In fact, some of the work I did, we worked with some of the people at E-Systems and with some of their code. So I'd like to show you the impact of computing based on a graph from this book. You see here, this is a graph showing the computation time for the discrete Fourier transform. The line down here, you can barely see it. It's just barely above the x-axis, is the time to compute using the FFT algorithm, the fast Fourier transform. This is called the discrete transform. In other words, if you just took a math book, looked up the Fourier transform, and just you implemented that formula in a computer program, this is how long it would run. Down here are the number of sample points. As you see, when you get to 512 sample points, the discrete transform, or in other words, the formula right out of the math book, starts becoming inefficient. When you get out to 1,000 points or even more, the discrete transform just takes off and becomes intractable. So it's the idea of looking for solutions like this to various computer problems that caused people to think about this whole issue of what sometimes is called tractability and sometimes is called complexity. The particular problem that I was working on, now I did some work in Fourier analysis back in the 1970s, based in part on some of the work by Cooley and Tukey and the work of some people at E-Systems and so on. As a result, I became aware of some of the techniques they used to try to break down the elements of a Fourier transform so that it could be done more efficiently in a computer. Later, I became involved in the analysis of digital networks. Basically, a digital network is a collection of gates. It can be represented by a directed graph, but it has a problem called reconvergent fan-out that makes the problem much more complex than it would otherwise be. Let me show you what I mean by that. Suppose you have a network of computer gates or logic gates like this. This is a simple AND gate, but it could be anything. This is just a representation. And suppose that an output goes to two different blocks of logic. And then later, those blocks of logic, at least one of the outputs of those blocks, and there can be multiple outputs, but at least one of them that contains this fan-out reconverges. In other words, the same signal goes through this path and through this path. It's what is called reconvergent fan-out. And it was one of the problems that I worked on. In fact, this was my PhD dissertation topic. And eventually I was able to solve the problem and compute the issue in what is called n log n time. I won't get into all the details. It was a very complicated situation and frankly consumed way too much of my life, I think. But at any rate, what it shows is that you can solve some of these problems from time to time with a little bit of insight. Now, it would be beautiful if someone could show that polynomial, that is p, is equal to NP. If it could be proven that polynomial solutions are also the same exact set as non-deterministic polynomial, just trust me on this, I'm not going to get into the proof. What it would mean is that the ability to verify a solution, in other words, if somebody walked in and said, here's the answer to the problem you're looking at, would be equal to or would imply the ability to produce a solution. In other words, the ability to check whether a particular result would be the same as the ability to produce that result. That could automate the search for solutions. In other words, basically the computer could do what we call today creativity. Typically, the way that people solve these problems is they work on them for a long time. Eventually, they get a little insight that enables them to reduce the complexity of the solution, like Cooley and Tukey did with the fast Fourier transform. That was sort of what I was doing in my PhD dissertation with regard to digital networks. If you can use a p-time algorithm to find a formal proof of any theorem, then you can verify any theorem in polynomial time. So if p was equal to np, we could imply solutions to all of basically the big computer problems. In fact, I'm going to leave you with a quote from Scott Aronson of MIT, and I'll read it to you. If p equals np, then the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. And I especially like the reference to Gauss because it turns out that despite the fact that it wasn't until the 1960s that much work was done on the fast Fourier transform, a lot of research has disclosed that Gauss had developed a very, very similar technique back in the 1800s. So everything that's new is not necessarily new. It may be that someone has thought of it before. At any rate, I realize this is not a typical video. It's completely outside the normal subject range. But I thought I would throw it in to inspire some people, particularly those who might be studying computer science or engineering, to keep this idea in mind. And if it particularly intrigues you, you might want to take this on as a research topic, for example, in the future. Because if you can prove that polynomial is the same as non-deterministic polynomial, you'll be one of the people mentioned in places like this, Mozart and Gauss. I hope that at least some of you have enjoyed this video and gotten a little bit out of it. I realize it's very hand-wavy, that was the intention, but nonetheless, I wanted to introduce people who may not have ever thought about the issue of complexity and computer algorithms to this subject. I hope you'll have a nice day and look forward to some future videos.